Okay, so in this section, we're going to be looking at the negative binomial distribution. Now, this is a generalization of the geometric distribution. In the geometric, we were only looking for one success, and there was only allowed to be one success, or we refer to it as the first success. Here, in the negative binomial, we're actually going to be able to choose the number of successes we're interested in. So any value, as long as there's a fixed value for that particular scenario, that's what we're looking for. So we can describe x as the random variable of the number of trials needed for a fixed number of successes. So for example, how many trials would I need to get 5 successes? And we can find the probability that it takes 10 attempts to get 5 successes, or 6 attempts to get 5 successes. Okay, let's look at the notation. There's no definite notation, but I'd like you to use NB for the negative binomial. 2 is going to be our R value. This is the number of successes we're looking for. And 1 over 6 is the probability of any individual success. So this statement represents the probability that it takes exactly 5 trials for me to get 2 successes. If we think about it, out of those 5 trials, the last trial has to be a success. Otherwise, I wouldn't have continued. So I can compartmentalize these and have the last value or the last attempt being a definite success, which means within these first 4 attempts, I'm going to need 1 success as well. So let's try and think of the probabilities that match those. What's the probability of 1 success from 4 attempts? Well, that just sounds like a standard binomial situation. So 4 attempts and 1 success, 4C1, success to the power of 1, failure to the power of 3. And once again, I know that that last trial was a success. So I can multiply by another p. Okay, we can just combine the expressions here. And we get just one expression this time, which looks like a standard binomial, but there are some differences that I really want you to be able to see. Mainly, the powers don't add up to the n value from the NCR statement, which you're used to seeing. So just be on the lookout for that. Don't let muscle memory take over. Be sure that these are different. Okay, let's just substitute in those probabilities, and really we just need to calculate this, and that will be the probability that we're looking for. The probability that it takes 5 attempts for me to get 2 successes. If we generalize this, this is what the probability function looks like. You can try to memorize that probability function, but really thinking through the little diagram and locking in the last trial as a success is going to be more successful for you, especially on more complicated or more complex questions. Okay, so let's walk through an example here. Philomena is practicing her piano scales. So piano scales are a little riff that you play on a piano, connected notes. Sounds quite nice. She's practicing. That's how you become an expert. She's practicing, and the probability that she's correct at any one attempt is 0.4. So x is going to be the random variable that represents the number of attempts needed to complete 4 scales correctly. So first we're being asked to find the probability that she completes her 4th correct scale on her 12th attempt. So let's start by actually defining the distribution. So x is going to follow a negative binomial distribution where we're looking for 4 successes, that's the fixed number of successes, and the probability of any individual success is 0.4. Okay, so in this first bit, we're actually looking for the probability that her 4th success happens on her 12th attempt. So the probability that x equals 12. Going to use the diagram once again to represent what's happening. The final attempt we know is definitely going to be a success. And in the first 11 attempts, we're looking for 3 successes. Okay, that should help us to write out the probability statements. The first part looks like a standard binomial probability. And then we once again multiply by a value of p for that final attempt. Okay, we can write this out simpler by combining the 0.4s. And then obviously we just need to punch this into a calculator, and the answer that we get to 4 decimal places, 0.0709. Okay, part B, let's be a bit more careful here. We're asked for the probability that she completes her 4th correct scale on the 10th attempt, given that her first scale was correct. So let me try and represent this in the diagram again. So I'm going to split this into a few more sections. I know what happened on the first attempt. She had a success. So I'll just split that into n equals 1. I know what happened on the last attempt. She had a success. And the variability is really in these middle ones. All right, so n equals 1 for the first attempt, n equals 8 for those in the middle, and n equals 1 at the end. We know what happens at the beginning and at the end. And we're looking for 2 successes in these ones in the middle. Okay, this is actually a given question. We've already been told that the first scale was correct. So we're not actually interested in that first one anymore. We're only interested in these 7 attempts that I've highlighted over here. So this is a new distribution now. From those 7, I'm looking for 3 successes. So y follows a negative binomial distribution for 3 successes with a probability of 0.4. What's the probability that my 3rd success happens on my 9th attempt? And we just plug these into the probability function, as we've been doing, and then into the calculator, and that gives us a final answer of 0.0836. All right, just make sure you're reading the question carefully. It was only at the end that we got the information that this was a given question, and really just thinking through what we would usually do with a given conditional probability question. We applied those same techniques here. So technically, we could have worked it out with the intersection divided by the probability of B, but really your intuition should let you know, I'm only interested in these outcomes. Let's go ahead and work out the probability from those. So now that we've seen how to find probabilities of a specific value, as in the probability that x equals 7, let's have a look at how we should approach cumulative probabilities or a range of outcomes. So just like this example, the probability that x is less than or equal to 10. Now I could go ahead and find the probability that x equals 10 plus the probability that x equals 9, 8, 7, 6 and 5 and add them all together. The reason we stop at 5 is because it's impossible to get 5 successes from 4 trials. I could add all of those together and that would actually give us the correct answer. But there is another way to think this through, and I'd like you to try to get your head around exactly what that means. Well, firstly, we know that we've had a minimum of 5 successes. And we're not sure how many trials it took to get those 5 successes. Was it 5, 6, 7, 8, 9 or 10? If it was 5, I may have had other results after the 5 that once again may have been successes, may have been failures. But the point is that I managed to get more or equal to 5 successes. The way I'm going to represent this is to actually define a new distribution. It's not that new. These 2 distributions coexist together. This is just going to be a standard binomial distribution where I have the number of trials, which are going to be 10, the probability, which is going to be the same 1/3, and the probability that the number of successes is greater than or equal to 5. Now that is equivalent to the probability that the number of trials is less than or equal to 10. If I can work out this, it will answer the original question, and together we get an answer of 0.2131. Okay, so if you like, I can generalize that for you and just say for any negative binomial distribution with parameters r and p, the probability that x is less than or equal to a is going to equal the relevant binomial distribution where the n value is a, p is the same p, and we're looking for the probability that y is greater than or equal to r. Now this relationship is always going to exist between the negative binomial and the standard binomial distribution. Now rather than trying to remember this as a standard result, I'd rather that you could just get the concept and in your head be able to go from the contextual negative binomial to the contextual binomial and vice versa. Okay, let me just see what would happen, or let me just show you what would happen for a greater than or equal to. So immediately we have a discrete distribution, and I know that a greater than or equal to can be written with a 1 minus. So I've got 1 minus the probability that x is less than or equal to 13. And we've just looked at how we would work out x is less than or equal to 13. We wouldn't be using the same binomial distribution because the n value for the binomial came from whatever was in the probability statement. So this time round, I'll have a different binomial distribution, I'll call it m, where the n value is 13 and the probability is 1 over 3. Alright, so I can find this probability now, the less than or equal to 13, because I know there's equivalent standard binomial calculation to do, and in our calculators we can work that out quite easily. So in this case it's 0.4480, and if I just follow through my 1 minus, I get 0.5520. Okay, spend some time to talk this through in your head, to check through the working out that I have here, and obviously when you get to the questions, the contextual questions that may well ask you to do this, make sure you understand the conceptual conversion from the negative binomial to the standard binomial. It's going to take a bit of practice, but you will be able to talk yourself through, to talk anybody through why they're equivalent and the equivalency itself.